8.1 is about exploring exponential models. Pretty much we got a new model in town. This is not linear, this is not quadratic, this is exponential, which means of course that the exponent is a variable. Your independent variable is an exponent. That's different. The linear variable has an exponent of it's a fixed exponent of 1, and the quadratic model has a fixed exponent of 2. This has a changing exponent, okay? Now, a couple things you need to notice about this formula. The value b will have a number there. That's called the growth factor. And when the growth factor is bigger than 1, then we consider the whole equation to be termed growth. This is what you want your bank account to do over time, folks. As time progresses on, you want your bank account to grow and grow and grow and grow. But that only happens if the growth factor is larger than 1. You'll also notice from this picture of the graph that A is the y-intercept. A is the y-intercept. So in your equation, A represents, you'll see that number, and you'll be able to identify the y-intercept very quickly. Another thing you'll notice is this graph gets closer and closer and closer and closer to the x-axis, also known as y equals 0. And that means that that line is called an asymptote to the graph. We talked about asymptotes when we were discussing the hyperbola and the inverse square function. Well, let's look at an example of how to graph this. So you're asked to graph y equals 2 to the x. Keep in mind that's really y equals 1 times 2 to the x. So your a value almost was disguised, but everybody in the room and everybody out there in TV land should recognize that that a value was really a 1. The b value, which is the growth factor, is a 2. If you start plotting points, making a table, not your favorite thing in the whole wide world, but oh well. You plug in a -3. 2 to the negative third power is 1/8, or 0.125. 2 to the negative second is 1/4, or 0.25. 2 to the negative first, we know that negative exponent causes the base to flip over, right? So instead of 2, it's 1/2. And 2 to the 0, we know anything to the 0 power is 1. Hey, that makes sense. The y-intercept is 1. That makes a whole lot of sense, that when you plug in 0, you get 1. Okay, when I plug in a 1, obviously I'm getting 2. When I plug in a 2, I get 2 squared, or 4. Plug in a 3, I get 2 cubed, or 8. So I can plot those values on here. Obviously, 3 giving me 8, that's an easy one to graph. 2 gives me 4, that's an easy one to graph. 1 gives me 2, easy, easy, not so easy, not so easy, really not so easy. To graph these real low points to the x-axis. But that's exponential growth. Now, we are going to get into story problems, another favorite part of your life. In this case, A, lost some light there. A represents the starting amount. For instance, we might have the starting population of a country, or the population starting in a particular year, or the amount of money that we start with in a bank account, or the amount that a bacteria population starts out being. I know that seems kind of weird, but sometimes we use exponential models for even bacteria. B, the growth factor, can be represented by this equation, 1 plus r, or I should say represented by this expression, 1 plus r, where r is considered to be the growth rate. The growth rate. B is always a positive number. Always, 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 always a positive number. R can be any real number we want it to be. In other words, it can be negative and it can be positive, depending upon whether the population or the money is going up or going down. We'll talk about the down part later. So how do they relate together? Well, let's say, let's suppose we start out with a percent change of, say, we are 20% increasing. A 20% increase translates to a decimal of positive 0.2. And when we add that to 1, we get a growth factor of 1.2. Seems pretty easy. Well, what happens if we have 1.75? Well, as a growth factor, that means that the growth rate was positive 0.75, so that must be a 75% increase. What if we had a positive 4? Positive 4. That would be a 400% increase. Now, what would that look like in the growth factor? Well, you take the decimal and you add 1 according to the expression there. 1 plus r. So the growth factor would be 5 in this case. Lots of kids mess that up right there. They see 400% increase. They know that r is 4, but for some reason they don't realize that it's b is 5. Or I give them the b value 5, and then they think that's 500% increase, which it's not. You have to subtract the 1 and then change it into a percentage in order to tell me the percentage increase. So let's look at an example with population growth. Let's suppose that the population of a particular country is growing at a rate of 1.24%. And let's suppose we start out with this population looking at the data from the year 1800. In the United States, there were approximately 5 million people. So how do we change that into an equation? Well, we have the starting amount. Now, it's not the starting amount from 0 AD. It's the starting amount from the year 1800. So as I've written over here on the side, X represents the years after 1800. So, for instance, 1900 would give me an exponent of 100. But if it was only 1850, then that would give me an exponent of 50. If it's the year 2012, that would give me an exponent of 212. So keep that in mind. The exponent has to be years after 1800. But this is the percentage increase. So the R value would be 0.0124. Notice that I changed it from a percentage to a decimal. And then the B value that goes with that, remember B is equal to 1 plus R. So the B value would be 1.0124. Kind of ran out of room there, didn't I? So we can find the model, and then maybe they'll say, so what is the population in 2012 according to this model? Well, so I have y equals 5 times 1.0124 to the 212th power, right? Because that's, so I'm gonna go to the handy dandy calculator here. 5 times 1.0124 to the 212th power. And that tells me that the population according to that model is 68.17 million. We'll just say that. Now, clearly the population rate changed in the United States since we have well over 300 million people in the United States. So that particular growth rate did not continue here in the U.S. Okay, example 3 which I'm going to tell you right now, I do not use the book. Can't even talk. The method from the book. Our book is really confusing on this particular problem, so I have a much better way of handling it. If you want to ignore me on this and look at the book, you'll be doing it a lot more difficult way, which I know a few of you will, because for some reason you like to make things more difficult. Anyway, so I have an equation, y equals ab to the x, and I have two different coordinates that sit on some equation. We have to find a and b. So we're trying to find an equation that has these 2 points on it. So I'm going to take these two coordinates and plug them in. So 4 is my y value and 3 is my x value. You notice I said write two equations and start with the highest x value. I promise you, if you start with the highest x value, you will more than likely be able to answer the question. And if you don't, you're going to get confused. Most Algebra 2 kids don't remember how to handle the negative exponents, and so it really confuses them. If we stick with starting with the highest x value, we won't have those kind of problems. So let's see. 4 equals ab to the third. And if we use the other coordinate, 2 for the y value and also 2 for the x value, we have these two equations. Now, in different problems in the past, we've done things like adding equations together. But in this case, since they're based on multiplication, we're going to divide these, almost setting up what looks like a proportion. But we're really dividing these two equations. And so what happens? Oh, I see a nice a's cancel out. Well, how many of the b's cancel out? 2 of them do. So this problem reduces to b to the first on the right-hand side, because we can subtract the exponents. Right? When dividing like bases, we subtract exponents. And 4 divided by 2 is the number 2. So now we know that b is equal to 2. How do you think we're going to find a? That's right. Plug it back into one of the equations. You got two equations. You might as well use them. 2 equals a times, we know the value of b, so I'm going to plug that in. Right? And so now we can simply divide by 4, 2 squared is 4 on both sides, and come up with our conclusion that a equals 1/2. So now we have the equation that we wanted. Y equals 1/2 times 2 to the x power. Remember, you have to plug your a and your b back into the original exponential function in order to write that equation. Well, what happens if the growth factor is a fraction between 0 and 1? Well, it turns into something called exponential decay. This is what you don't want your money in your bank account to do. It is, however, what most of our cars do. They depreciate. You've heard the term depreciate? Well, that's the same idea. They lose value by a percentage over time. Of course, the y-intercept is still a, and the y equals 0. The x-axis is still the asymptote to the graph. It just looks kind of backwards from the exponential growth model. You're going to have to be able to look at these equations and tell me whether you think they're exponential growth or decay, just by looking at the equation, nothing else. And I will tell you the secret lies in looking at the value of b. As soon as you see that this is a fraction, or something smaller than 1, we know that this is decay. As soon as you see this is larger than 1, you know that this is growth. Keep in mind, I'm not really paying any attention to the a value. That has nothing to do with determining growth or decay. I look at the value. As soon as I see that it's smaller than 1, I know that the answer is decay. In example 5 in our book, it's pretty pointless. Since y equals 0 is the answer to all of them, trying to determine the asymptote to the graph, you should know when you look at any of the exponential growth or decay models that the asymptote is y equals 0. That should not be a difficult question for you to handle. Okay, example 6. Handle this the same way we did as example 3. You're going to be looking at a graph. You're going to need to pick out 2 points off the graph. If I were you, I would always pick the y-intercept if possible. The y-intercept makes things a lot easier. So for instance, if you are looking at example 6 in the book, you can see that I picked the y-intercept 0, 20,000 and 1, 17,000. Now, You can pick any points that you want, but you'll make your life a lot easier if you pick the y-intercept, because as soon as you pick the y-intercept, you immediately know the a value. As soon as you know the a value, you can use it. For instance, on the next equation, I plug in 17,000 for y and 1 for x. Well, I already know the value of a, right? That's 20,000, so I'm going to plug that in here, 20,000. And then I'm going to divide, obviously, in order to come up with the value of b. Oh, let's see here. That should be easy. 17 divided by 20. I shouldn't really have to think about this, but oh well, I am. 0.85. So you would have your equation, y equals 20,000 times 0.85 to the x. Is this growth or decay? Everybody should be screaming decay, right? Because the growth factor in this case is negative 0.15, or a 15% loss. Every year we're losing 15% of the value. We're only keeping 85% of the value. And I'll finish this. Let's take a look at a few more of these. Suppose that you have a rate or an R value of negative 0.2. That really translates into a 20% loss. Or you could say the word decay. Now, in terms of b being 1 plus r, well, if you add 1 to this value, you get 0.8. So the growth factor is really more about what you're keeping than it is about what you're losing. So you're keeping 80% even though you're losing 20%. 1.7. That would be an R value of positive 0.7 or a 70% gain. That's what you really want your money to do. A 9% loss. That would be negative 0.09. If you add that to the number 1, you get 0.91. So if you're losing 9%, you are keeping 91%. Likewise, 5 is a 500% increase or gain. I guess I could use the word increase. And if you add that to 1, that means you have a growth factor of 6. Lots of students make mistakes here. They have a growth factor or they have a rate that's bigger than 100%. And so they forget, and so they put 5 here instead of 6. Or they think that 6 means 600% when it really only means 500%. See it?